Hello all. Welcome to the second lecture regarding to classification of signals. So in the previous lecture we had seen about the basics of signals and introduction of signals, and in this particular lecture we are going to see with classification of signals. So these signals, if you go to the basic extent, they are being classified as analog signals and digital signals. The signals are classified as analog signals and digital signals. These analog signals are called as continuous time signals, and these digital signals are called as discrete time signals. The property of analog signal is such that the signal values vary continuously with respect to time. The time may be milliseconds or microseconds. You may go to any downscaling of time. At every instant of time, there would be a change in value. So it is called as a continuous time signal or analog signal. You can remember only one thing. In analog signal, the value of signal is going to vary continuously with respect to time. And in these analog signals, one more important property is that it always consists of an infinite set of values. That is, there is no limitation to values. You can go to any micro level and you can find out the value of the signal at that particular instant or at that particular point. So that is why these continuous time signals, what happens is they essentially contain infinite set of values. So we will be seeing the representation. And digital signals, the main property of digital signals is the digital signals only will have two values, that is 1 and 0. The definition of a digital signal or discrete time signal will go as follows. If the signal contains a discrete set of values, discrete means it is not continuous. So it is just opposite of analog signal. Discrete is something which is not continuous. So if the signal contains discrete set of values with respect to time, here also it is with respect to time. You can observe in these subject signals and systems, everything is with respect to time. So continuous time signal by definition itself, it is given, that is scaled to time, and here discrete time signal also with respect to time. So everything is scaled in accordance with the time. So if the signal contains discrete set of values with respect to time, it is called as a discrete time signal or DTS. And the main difference between a discrete time signal and continuous time signal is a discrete time signal contains a finite set of values, and continuous time signal generally it consists of infinite set of values. And the process through which continuous time signal or analog signal is converted to digital signal is called as sampling. It is called as sampling, and here we will be seeing the continuous time signal, and this is the difference between continuous time signal and discrete time signal. So this is CT signal. This is continuous time signal. Its value is varying with respect to time. And digital signal would be, see, at -2 it is having a value. At -3 and -1 the value is 0. That is, it is not having any value. And at 1 and 2 its value is 0, and at 3 and 4 its value is 1. It is having some value at that particular point. So that is the, let us see the tabular form or graphical representation or functional representation or tabular representation. Let us see. You will be getting an idea if you see one form, one type of representation of a signal. You will be getting an idea how to define its values. A discrete time signal x of n signal is defined as x of n here is a function of a integer variable n. In the DS processor, that is digital signal processor, the signal is represented by discrete encoded values with a finite precision. And see, if you see the graphical representation of a discrete time signal, Okay, at -2, at -1, nothing is there, and at 0, it is having some value. Suppose say x of 0. Let us say the value is x of n and n is 0 here. So here substituted 0 as the value here. We will define it as x of 0. Now here it is x of 1, and here it is x of 2. Here it is x of 3, and here it is 0 again. No value is there. Now here it is x of 1. The function is defined as x of 1. The value of amplitude is okay. The value of amplitude is also 1 here. So in digital signals, what happens is wherever there is a presence of a signal, the value would be 1. Now here also the same. Now here it is x of 3, but it is towards the negative side. It is towards the negative side. Okay. Now functional representation. Functional representation. It would be given as x is equal to 1 comma 4 comma 0. It is 1 for n is equal to 1 comma 3. It is 4 for n is equal to 2 and 0 elsewhere. Suppose this particular representation means that when the value of x of n is 1 and the value of x of n is 4, for n is equal to 1 comma 3 and for n is equal to 2, and it is 0 elsewhere. That is, if for different values of n, that is rather than 1, 2 and 3, elsewhere the value is 0. Now n and x of n, suppose let us take the values of n. N we will take it as time, suppose, or we will be taking the values of x of n. Suppose see here -2, -1, 0, 1, 2, 3, 4, 5. Now the values of x of n here given. This is the value of the signal. So these are the different ways by which a signal is being represented by different forms. And mathematically means by using equations. X of n, that is x of n is defined as the discrete time signal is equal to x of t, where t is the time period and where t is equal to nt or x of nt, that is n times t. Now basic types of signals. Let us see the basic types of different signals. Now this is called as, this particular type is called as a unit step function. Unit step function. That is, a unit step function is defined as u of t. That is where u is the unit and t is the time. It is defined as u of t is equal to 1 when t is greater than or equal to 0, and it is 0 when t is less than 0. Suppose if you observe in this particular picture, the value of this unit step function is continuously, its value is 1 when the time is greater than or equal to 0. At 0 also the value is 1, and after 0 also the value is 1, and it is 0. That is, it is not having any value when time is less than 0. This is the thing. This step function is normally, it is used as a test signal, and you can see that if the value of unit step function, if it is equal to 1 when t is greater than or equal to 0, this area under this step function would be unity. Unity means it would be continuously, and there is no end for that particular area. Okay. Now next, unit impulse function. This is one of the most important signal in signals and systems. The impulse function, this is represented by tau of t, okay, where t is the time period. It is equal to 0 where t is not equal to 0. That means if you go to the negative side or if you go to the positive side, the value of impulse function is 0 throughout the time factor, and when time is equal to 0, exactly it is equal to 0, the value of impulse function would be infinite. Infinite value you will be getting. Okay, so here you can see at 0 it is having unity value, or you can say that it is infinite value. And suppose see, integral minus infinity to infinity, that is you have taken the left extreme and the right extreme of the number system. Integral minus infinity to plus infinity, dou of t is equal to u of t, that is unit impulse function. Now you can write it as dou of t is equal to d by dt of u of t. You can remember it as u of t is differentiated with respect to time. That is, this you can write it as d by dt of u of t. So this is the unit impulse function, where it would be having an infinite value at 0, and at all other time values its value is 0. Okay, now let us see some more details about this particular unit impulse function. This function is theoretically undefined. It goes to infinity for an instant, but it does have an area of 1. That is, it is having an area of 1 at that particular instant, where the time period is equal to 0. So remaining throughout the integral, the value of impulse function would be almost, it would be 0. So this is a basic unit impulse function. In the next lecture, we will be seeing different extension to different types of signals.